Okay, hi. My name is Ebrahim MolavianJazi. I work with Nick Laneman at Notre Dame. This problem is about multiple access channel in finite block length regime. So what we do is that the main argument is that classical information theory deals with n approaching to infinity, but we focus for delay limitations and complexity limitations on finite n. So for a simple and but important problem, which is a two-user multiple access channel, the results can be extended to more users, several users. So the point is that these mutual information random variables can characterize the three error events of the for a two-user MAC, which is like one user being in error, or the other user being in error, or both user being in error, and T here is the time-sharing random variable. And what we know as in the classical information theory is that, for example, Alsvide gives this result on Leo, so that the expectations of these random variables characterize the capacity region for infinity and epsilon going to 0. And here is like a typical shape that we have, like a pentagon shape is usually shows this thing. And I mean, in general, it may be the convex closure of all these all such pentagons. So the proof usually goes as random coding and joint typicality decoding, where you compare these mutual information random variables with their expectations. So there is nothing essential to looking at expectations. We can use any general threshold and compare with that. So for n growing to infinity, the PDF of the mutual information random variable concentrates about the mean. So if you operate below the mean, the channel can support. There is no outage, as we call your code word will look typical. But if you are above that mutual information random variable, so it will not look typical, and there is an error probability of 1. So what happens in n finite is that we can approximate this mutual information random variable PDF with a Gaussian shape. So wherever you choose your rate, there will certainly be some outage probability, because there are some channel realizations that cannot support the target rate that you have chosen, for example, here. So we will have 3 of them. A union of these 3 outage events for each of the error probabilities characterize these the error, and so we could use actually union bound to split that between like the 3 outage events. And there is of course a confusion probability which says that there is another code word which is typical or which is passing this LRT. Turns out that if this is vanishingly small and we assign all the error probability to do it into the outage events, we achieve the highest rates. And so what we do is that using this union bound, we have like 3 outage events, and we split that error probability epsilon that we are given between these 3 error events. So we have lambda 1 epsilon, lambda 2 epsilon, lambda 3 epsilon for each of the error events. And so we will have like, so this is a Gaussian, the Q inverse function, the means and the variances or so-called dispersions can characterize the region. So there is a penalty term that is characterized by the finite block length, the dispersion terms, and the Q inverse function and the error probabilities. So for a simple example of Bernoulli for binary inputs, real addition with Bernoulli 1/2 for this error probability and these ends, we can see that the region is a curve as opposed to the corner shaped of the classical region. And as n grows to infinity, it will be more similar to the classical region corner shape. And you could see that, I mean, this is, at least in this example, it holds that this is here, for shorter ends, they are more noise limited. As n grows to infinity, they become more interference limited. And so there is a recent work published a couple of weeks ago by Tan and Cossett that look at the same problem. They do not split as we do. They do not use this union bound. They look into a 3-dimensional Gaussian for a 2-user. For an M user, it is like 2 to the m minus 1-dimensional Gaussian. They need to look at the covariant matrix of these number of dimensions and the Q and a Gaussian random variable of that order, which is very complex to calculate with these scalar random variables and with this splitting. So we can get the same results, and the loss is very little. And now it is a couple of months that we are working on the converse. We think that this region, or the one that they have, that Tan and Cossett have in their paper, should characterize the actual region, and this may get the converse. Thank you.